Okay, still in chapter 9. I am pretty sure this is the last video. I think we can get it all done today. So that's what we're going to do our very best to do. So chapter 9, where are we going to start? Well, let's talk about kinetic theory of gases. This is kind of theoretical, but we'll do the best we can to kind of explain what's going on here. So kinetic theory of gases, the models that I drew for you at the very start of the chapter of a solid, a liquid, and a gas, actually all that is derived from this kinetic theory of gases. Okay, and mathematically, the kinetic theory of gases says each translational is equal to 1/2 times the mass times the velocity squared, and that's equal to c times t. Okay, well, let me try to explain that. Remember, we talked about gas molecules, and we said that most of the energy in a gas is tied up into translational motion. A gas particle can vibrate, it can rotate, and it can also move from here to there. But we said that most of the energy is actually tied up in the translational motion. We could ignore the vibrational, the rotational, and we can get away with that for a gas. So how do I calculate the translational energy? Well, it's kinetic energy, and whether it's a planet, a block of wood sliding down an inclined plane, or a little tiny molecule, the laws for physics apply equally. So to calculate the translational energy here, which would be pretty much the total energy there, that's kinetic energy, and that's 1/2 times the mass times the velocity squared. Okay, so m here is the mass of the molecule, technically actually in kilograms, although we probably won't use this for any math in here. U here is the average speed. Okay, we're using U here because V is already taken. We've got volume on that one, so that this will keep you from getting too confused. And U here is the average speed, all right? Because it turns out not all molecules in a gas are moving at the same speed. And there's a distribution, and I'll show you that in a minute. C here is a constant, which has the same value for all gases. And then T, of course, is your temperature in Kelvin. All right? So what do we mean by this average speed, and why do we have to take that? Well, if you were able to look at a gas, and you were able to look at every single molecule in the sample, and you were able to measure their velocities or their speeds, and you could count them all up, this is what you would get. When gases are at lower temperatures, not every molecule is traveling at the same speed, but there's a distribution. At lower temperatures, there's less of a distribution. Okay, and so I've got a large fraction up here, and then it kind of goes down to here. All right. At higher temperatures, what happens is your distribution widens out a little bit, but your average is still higher. So here's your average here for maybe a gas at lower velocities here. Here it is at a higher velocity. Here it is at higher and higher. And notice as my molecules are moving faster, in other words, have more energy, the distribution is wider. There's a larger range of values that you could have. That is actually a concept called entropy, which is the amount of disorder in a system. And we'll actually talk about that next semester. But that's what happens. Okay, things kind of widen out as the gas gets more energetic. All right. Now, that's why I can't just say it's the velocity because, well, which velocity, right? So this is actually not the average velocity, okay? Because notice this curve is not a perfect bell curve. It kind of goes up sharply and then it kind of tails out. See this one same way? Out here, it's just wider. So this is actually called the root mean squared speed, and it's actually the most probable speed that the molecule would be at. Okay, your average, since this is actually kind of widens out there, is actually somewhere over here. Okay, but we're not going to worry too much about the difference between the root mean squared speed and the average speed and all that mess. It's just not that big a deal. All right, but that is what we're talking about here when we're talking about average speed. Okay, all right. Well, 1/2 times the mass times the velocity squared. There's your translational energy. That's equal to c times t. All right, now what does that all mean? Well, c here is a constant, so that's a constant for, all gases here. All right, if I have a gas and I heat it up or cool it down, Does the mass change? No, the mass is still the same. The 1/2 is still the 1/2. So there's really only two things that can change in this equation, and that is average speed and temperature. Do you see that if I raise the temperature, what happens to the average speed? The average speed goes up. If my molecules are moving faster, that means a higher temperature. So, in the grand scheme of things, this is what that means. Temperature is directly proportional to the average speed of the molecules. In other words, what I could do, theoretically, is I could take this axis here that says velocity, and I could scratch that out, and I could write temperature, and I could put degrees Kelvin here. And I'd get the same distribution. So not every molecule in a gas has the same temperature. When you stick your thermometer in there and you measure the temperature of that gas, your thermometer is actually taking all the molecules, taking an average speed, converting that to a temperature, and showing it on the thermometer. Your thermometer is a lot smarter than you thought it was, isn't it? All right? So when we said back in chapter 1 that when you measure temperature, you're not measuring heat content, what you're doing is you're measuring the average speed of the molecules. That's your Kelvin degrees. Heat content is joules and kilojoules. But yeah, that's not every molecule has the same quote-unquote temperature. There's a range. And the hotter it is, the wider the range. Okay? And that's really all that is saying. There's a relationship between the speed and the temperature of a gas. All right? Okay, well, how can I use something like that? Well, here's one way you can. This is something called Graham's Law. Okay, and Graham's Law relates the mass and the speed for two different gases, same temperature. Okay, now, the temperatures have to be exactly the same. If your temperatures aren't the same, your kinetic energies aren't the same, and this whole thing just kind of blows up. But if I've got two gases at the same temperature, both of these relations hold. All right, there are two forms of Graham's Law you need to know, all right, depending on what they give you in the problem. The first one looks a little something like this. The time it takes for gas 1 to travel from here to there over the time it takes for gas 2 is equal to the square root of the molar mass of gas 1 over the molar mass of gas 2. All right, the square root is here because remember that the kinetic energy depends on the mass, but it depends on the velocity squared. And so that's why you got to put the square root over here. All right, but sometimes they won't give you a time, they'll give you a rate of speed. How fast is the gas traveling? So that equation looks like this. The rate at which gas 2 travels over the rate at which gas 1 travels is equal to the square root of the molar mass of gas 1 over the molar mass of gas 2. All right, notice that there are two different equations, and that's because the problem, sometimes they'll give you a time, sometimes they'll give you a rate. Notice this is 1 over 2, 1 over 2. This is 2 over 1, 1 over 2. All right, and the reason why is because if I have a very light gas, very light gases travel very fast at the same temperature. Very heavy gases travel very slow at the same temperature. Why would that be? Well, because if I have two gases at the same temperature, then that means their kinetic energies are the same. See? So 1/2 times mass times velocity squared for my first gas would be equal to 1/2 times mass times velocity squared for my second gas. Well, if my first gas, if this number is really big, and for my second gas, that number is really small, mass-wise, what has to be true about the velocities if they're going to be equal? Well, this velocity must be relatively small. This velocity must be relatively large. So large mass, smaller velocity. Small mass, larger velocity. And that way your kinetic energies of your gases are the same because they're at the same temperature. Now, if they're not the same temperature, then again, all bets are off. But if they are, that's the way it works. So lighter gases travel faster. It's like football players. Think of it that way. You get them out there and you start them on the goal line, you run a race, and you let them run to the other side of the field. Well, after about 20 yards, the wide receivers start to pull away, little light guys, that are running down the field. and your linemen, your big lumbering guys, are just kind of, lumbering along. After about, 30 yards or so, then, the linemen will just quit running because, they don't ever run that far. Your wide receivers are out in front, and, your running backs are maybe right behind them, and, your linebackers are kind of bringing up a little bit there, and so on and so forth. And, by the time they run to the other end of the field, it's probably going to be pretty easy to see who your wide receivers are. Well, your wide receivers are little fast guys, just kind of June bug around all over the place, and they don't ever get hurt because no one ever hits them solid. But, God help them if someone ever hits them solid, because it'll crush them. Linemen, it's pretty easy to hit a lineman, but, they're just so big, you just bounce right off. You can't really hurt them too much there. Well, it's the same way with gases. Big, heavy gases travel slow at the same speed, at the same temperature. Lighter gases travel fast. Okay, and it all comes back to they have to have the same kinetic energy at the same temperature. That's why. All right. Light gas, low mass, is going to take a very short time to get from here to there. Heavy gas is going to take a very long time to get from here to there. Directly proportional. 1/2, 1/2. A light gas, low mass, is going to travel at a high rate of speed. A heavy gas is going to travel at a low rate of speed. Inversely proportional, 2/1, 1/2. The key to doing Graham's law problems is first read the problem, figure out what they're giving you. Am they giving me a time, or are they giving me a rate? Choose the proper equation, and then it doesn't matter what you let be gas 1 and let be gas 2, but you have to be consistent across the equation. Don't get your 1s and 2s mixed up. All right, so for example, a certain gas takes 2.42 times as long to effuse, and effuse means to travel through a membrane or through a small hole into something else, as nitrogen at the same temperature and pressure. What is the molar mass of the gas? Okay, so see, here's another way that you can figure out the molar mass of a gas without knowing, what the formula is. So the second way, besides the Dumas method there that we talked about. So the first thing I got to ask myself is, okay, what are they telling me here? Are they giving me a rate, or are they giving me a time? Well, let's look at the problem. So it says this gas takes what? 2.42 times as long to get from here to there. Is that a rate, or is that a time? That's a time. 2.42 times as long. See, if it said 2.42 times faster, it was traveling faster, that's a rate of speed. But 2.42 times as long, that's a time. Okay, so which equation am I going to use? Well, I'm going to use the time 1 over time 2 is equal to the molar mass 1 over the molar mass 2 square root. Okay? All right. Second thing we got to make a decision on is, what are we going to let be gas 1? What are you going to let be gas 2? It really doesn't matter as long as you're consistent. But generally speaking, in problems like this where they're asking you what the molar mass of the gas is, I like to let the unknown be gas 1, because if you do that, what that does is that puts your unknown up here in the numerator instead of the denominator, and so I don't have to multiply by and try to get it out of the denominator. It's one less step math-wise. But really, it doesn't matter. You could do it either way, and you could solve it either way. It's still going to work. All right. So I'm going to let gas 1 be the unknown, and that means my nitrogen would be gas 2. Okay. So do I know how long it takes for that gas to effuse from here to there? Did they give me a time? No, they didn't give me a time. Do I know how long it takes for the nitrogen to get from here to there? Well, they didn't give me a time there either. No one gave me any seconds or anything like that. I can still do this problem because I know a relationship between how long it takes for the gas, the unknown, to travel versus how long it takes for the nitrogen to travel. So if this takes 2.42 times as long as the nitrogen, let's call the nitrogen X. It takes X amount of seconds to get from here to there. So if the time for the nitrogen is X, how long would it take the unknown to get there? Well, 2.42 times X, because it takes 2.42 times as long, see? All right, so the time for this will be my unknown, this will be my unknown, this will be my nitrogen, This will be my nitrogen. Make sure you get your 1s and 2s straight. So 2.42x, there's my unknown, over x, that's how long it took for the nitrogen, is equal to the square root of the molar mass of my unknown over 28.02, and that's just the molar mass of nitrogen. Just add up 2 nitrogens here, and we come up with something like this. Notice if we do that, our x's cancel. See, and I get 2.42 over 1, just 2.42, is equal to the square root of the molar mass over 28. So as long as I know a relationship between the two, you can still do the problem. If they gave you the seconds, plug the seconds in. But if they gave you a relationship, express one in terms of x, call one of them x, and express the other in terms of x. And that works too. All right? Okay, well, now we need to solve for molar mass. So I got that square root. How do I get rid of that square root? Well, we're going to square both sides. When I square the square root of molar mass over 28, what do I get? Well, I just get the molar mass of over 28.02. You know, you get rid of the square root. But if I square this side, what do I have to do over here? I also have to square that side. So this ends up getting rid of the square root. This is 2.42 squared, whatever that happens to be. I want to solve for molar mass, so what am I going to do? I'm going to multiply both sides by 28.02, get that out of here and over to the other side. So that's exactly what I did here. I just switched things around, you know, there. So 2.42 squared times 28.02, your molar mass is 164 grams per mole. And there's your answer. Make sense? So what is it? Don't know. You know, I don't have any other information about that gas at this point. Could be anything, but I do know its molar mass is 164 grams per mole. So maybe I can go about trying to find the simplest formula, maybe use that molar mass, and then somehow figure out, you know, what to do from there. And that's how Graham's law works. Side note, Graham's law, you would look at Graham's law and you might think, wow, this is a really useful thing. You know, maybe I could apply this to a lot of things. Let's say, for example, you know, I've got a tank, and maybe the air is leaking out of the tank. You know, well, maybe I could use Graham's law to figure out how long it would take for all that air to leak out of the tank. You know, look at the molar mass and, you know, this and that and so on and so forth. And you might think that would be useful. Well, it's really not, okay? And this is the problem with Graham's law. In Graham's law, there's 2 things that you're ignoring, all right? The first thing you're ignoring is the diameter of the appeter. Okay, so in other words, if I've got a gas and it's going through a hole or something and leaking out into space or whatever, there's crowding at the hole sometimes if your hole isn't big enough. You know, if we were all in the lab and I said, you know, you have 10 seconds to get out of the lab, could you get out in 10 seconds? Yeah, I think you probably could. You could probably make your way to the door and get out of there if if your life depended on it, right? Hopefully it won't have to someday. But if I said everybody has 10 seconds to get out of the lab all at once, what's going to happen? Well, everybody's going to hit that door at the same time, and everybody's going to be crowded at the door trying to get out the door, and that's going to slow you down. Well, Graham's law does not take into account a real-life situation, something like that. All right, just to make it fun, tell you what, this time I'm going to say you've all got 10 seconds to get out of the room, but the next lab section has 10 seconds to get into the room. Wow, that sounds like a lot of fun. So you're trying to get out the door, but what are you running into on the other side? Well, you're running into people fighting, trying to get through the door. Well, that's really going to slow you down. So, you know, if I have a tank and it's got a leak in it, and it's leaking the gas out of the tank, your little gas molecule, you're in the tank, so you're swimming toward the hole, you know, swimming toward the light there. What do you see on the other side? Well, you see air. You see other gas molecules, and they're in your way. See, and that's going to slow you down. So from a practical standpoint, Graham's law doesn't work well, unless the diameter of aperture is not a problem, and maybe you're leaking into a vacuum or something like that. All right. So Graham's law looks a lot more useful than it probably really is. Now, is the principle sound? You know, the heavier the gas I have, the slower it's going to travel. And the lighter the gas I have, the faster it's going to travel. Yeah, the principle is absolutely sound. Could I use a Graham's law-like law, maybe, to figure out any kind of an engineering problem like that? Yeah, you probably could. Okay, but it's just probably going to be a little more complicated than this right here. But this is as complicated as we're going to get on that. Okay? All right, well, you know, I spent all this time teaching you something and then spent another 10 minutes tearing it down. Does that mean it's really totally useless? Well, no. Graham's Law actually won a war. Okay, so story time. This, by the way, is one of my best stories, so I saved it for last. So, you know, it's 1942, so 1941. What's going on in 1941 in the world anyway? Well, a little something we like to call World War II, right? So who's fighting this time? Well, it's the Germans. Germans were just kind of hard to get along with in the 1900s for some reason. It's just a bad century there. And the Italians and the Japanese, and then on the other side you've got the Americans. You've got the British to some extent. You've got the French, and you know others. And so that's pretty much your Axis and Allies powers there. And so we're fighting. So here's the problem. We found out that you can use uranium to actually build an atomic bomb. All right. Well, turns out the Germans know this too. So there's a place in Tennessee called Oak Ridge Laboratories. And it's secret. Nobody knows about it. By the way, you can still go there today. There's a town that grew up around it. You can go to Oak Ridge, Tennessee. Dr. Pat actually worked at Oak Ridge Laboratories for a couple of summers there. You know, so yeah, ask her about that. It's pretty cool. But you're working at Oak Ridge Laboratories and you're trying to develop this atomic bomb. Okay, and guess what? There's a classroom of Germans over on the other side of the ocean here who are working on the exact same problem. All right. So here's what you need. You need uranium. Okay, no problem. All right, it's not real plentiful, but we can get it somehow. But you need a special type of uranium. Remember that not all atoms of the same element have the same number of neutrons. You have isotopes. Some weigh more than others. And so there's uranium that weighs 235, and there's uranium that weighs 238. Which one of those is more plentiful? Well, the 238 by far. You know, much more plentiful. 99% of it at least is uranium-238. Which one do you think you need to build the bomb? Well, yes, uranium-235, the one that you don't have a lot of. Okay, 238 is useless. It's not going to fizz and break apart and give me the atomic bomb. I need that uranium-235. So basically, what we're going to do is we got to figure out a way to separate the uranium-238 from the uranium-235. And if I can do that, I can build a bomb, I can win the war. All right? Well, again, guess what? The Germans know this too, so they're working on it as well. So you've got to figure out a way to separate the uranium-238 from the 235, because the 235 is what you need. And the Germans know this too. So they're working on something over there. You're working on something over here to figure this out. So what are you going to do? By the way, if you had money to bet on this, who are you betting on? Are you betting on you or the Germans? Well, I'm betting on the Germans. They're just smart people, man. They, had a major professor once said, anything you can figure out to do now, some German did back in, 1914 with a piece of toilet paper and a rubber band. They're just smart. They're really good at this stuff. And so, yeah, most of the physicists over there, Germans. So, yeah. But, hey, we got to try, right? That's why they play the game. All right. So what are we going to do here to get that uranium-235 separated from 238? Well, you're a chemist, so maybe we could use something like that. So fluorine. Fluorine, very highly reactive gas. Reacts with uranium, forms this really nasty, toxic, heavy gas called uranium hexafluoride. So what happens if I react uranium-235 with fluorine? Well, I get uranium-235 hexafluoride. What happens if I react uranium-238 with fluorine? Well, I get uranium-238 hexafluoride. So is there anything I can do to separate those chemically? Well, no, because uranium's uranium. See, it doesn't matter how many neutrons you've got there. What makes uranium uranium and what makes it react the way it does is the number of protons. And so that's not going to work. But I got all this uranium-235 hexafluoride laying around, and 238, this big mixture. Maybe I can do something with it. Okay. Well, this is actually what they did. What they did is, remember we're talking about Graham's law here? All right. So I've got uranium-235 hexafluoride, I've got uranium-238 hexafluoride. Which one of those, if I let them travel across a certain distance, which one of those would travel faster at the same temperature? Uranium-235 hexafluoride or uranium-238 hexafluoride? Well, the uranium-235 hexafluoride would, because lighter gases travel faster than heavier gases at the same temperature. Graham's law. All right. Now, is there much of a difference? No, there's not much of a difference. You know, your difference in mass there, about 0.4%. So it's like taking two runners that run just essentially the same speed, but one guy's just a hair faster than the other. If you let them run for about 20 yards, they're probably still neck and neck. After 50 yards, they're still probably right there. But after 70 yards, maybe the first guy is just a barely a half step in front of that other guy. And maybe by the time they get to the other goal line, maybe he wins by a full step because he's a little bit faster. The longer you run the race, the more those will separate out from each other, right? Okay. Well, that's exactly what they did. And your book has a fairly decent picture here somewhere. And this is actually how they purify uranium, sort of like this. So here's our uranium hexafluoride going through the tube. And then you've got this porous barrier here, so it lets some of the gas go through. And so what happens is the uranium-235 hexafluoride diffuses through these little holes in this porous barrier faster than uranium-238 does. And so it gets kind of trapped over here, and so therefore it comes out over here. The uranium-238 doesn't diffuse through the porous barrier as fast, and so it just goes straight through. By the way, this stuff is so nasty, it eats through those membranes, and they got to replace those membranes like every 24 hours because it just eats through them. You know, really bad, really nasty stuff. But what should happen, theoretically, is the gas that comes out through here is going to be highly enriched in uranium-235 hexafluoride. Now again, you know, we talked about this. There's a range of velocities gases have at a certain temperature. So you probably have some fast-moving uranium-238 hexafluorides making it through with some uranium-235s, and you probably still have some slow-moving 235s making it through over here. Okay, but the gas coming out of here ought to be very highly enriched in uranium-235 hexafluoride relative to uranium-238 hexafluoride. All right, and that's what they did, and that's how they figured it out. All right. And we figured it out. The Germans didn't. That's why you're not speaking German today. In reality, who actually figured it out? Well, it was actually our Germans, not their Germans. See, a lot of these Germans, not only were they German, they were also Jewish. And, you know, these guys are not stupid. They're smart. They know what's going on. And so what they did is they hightailed it over to Switzerland, you know, as fast as they could, you know, when things started going really, really bad over there. And from Switzerland, they ended up over here, and they actually went to work for us. And so it's basically kind of our Germans versus their Germans. Is kind of the way it worked out. But yeah, you know where they stuck them? They stuck them over in Los Alamos, over in New Mexico. So, you know, you come from Germany and you come to America, you think, well, where do I want to go in America? Well, I want to go to Hawaii. You know, that'd be nice. Or Florida would be kind of cool. So where'd they put them? Well, they put them out in the middle of the desert in New Mexico at 110-degree heat. So do you imagine maybe they were kind of regretting their choice after a summer in New Mexico? I don't know. But yeah, it beats being over there because things were not in a good way, you know, in 1941 in Nazi Germany. Read the book. You'll find out about it. All right. But yeah, that's kind of what happened. And yeah, we figured it out. In reality, we really didn't even need it to beat the Germans. because the Germans attacked the Russians and us at the same time. Never attack two different people at the same time. Fight one war at a time if you can. And yeah, they almost got to the Russians. They were within sight of the capital city, Moscow. But then the winter, which happens to everybody that invades Russia, they always get bogged down in the winter for some reason. Nobody ever learns. Hit them. And yeah, the Russians came back, and man, they were coming hard toward Berlin. And they were mad. They were really mad. And the Germans were just practically, just doing everything they could to surrender to the Allies before the Russians got them, because it was going to be really, really bad if the Russians came through. And so, yeah, that's pretty much how that ended. We did get a chance to use this, but not on the Germans, but actually on the Japanese. And so that was the bomb that was dropped on Hiroshima and one on Nagasaki and so on and so forth. And, you can make a case for, should we have done it, should we have not done it? I get it both ways. But this is not a government class, and, whichever opinion you have is okay with me. Doesn't affect your grade. But yeah, that's where it actually came from. It came from this. And this is the way they actually enriched that uranium. All right? To make nuclear fuel, by the way, if you're making fuel rods for nuclear reactors, you need about 2 to 5% enriched uranium-235. Natural occurring is 0.72. So really about 99.3% of uranium is uranium-238, which is the useless stuff, and uranium-235 is the good stuff, and there's not much there. But you don't have to get it all the way. If you can get it to about 2 to 5%, you can actually use that for nuclear fuel and nuclear power plant. If you want to build a bomb, about 80%. Okay, and there are certain theoretical papers that will say, depending on your bomb geometry and this and that, 25% might be the lower limit if everything goes perfect. Okay, but 80% is weapons grade uranium for nuclear bombs and things like that. So there's no way you can accidentally make a nuclear weapon. You can't do it. You can't sit there and enrich uranium for peaceful purposes for nuclear power plants and it's like, oh, we went too far, got to 80%, didn't mean to do that. No. You have to be trying. You have to be trying really, really, really hard to get a nuclear weapon. You can't accidentally do it trying to make nuclear fuel for a power plant. So when a country tells you that, oh yeah, we're just doing this for research purposes and this and that, and they're up around 10, 15, 20% or something like that, that's way overkill for a nuclear power plant. They know they're lying. You know they're lying. They know that you know they're lying, but that's just what they say. But yeah, you can't accidentally get there. You've got to try really, really hard to get to 80%. But if you can get to 2 to 5%, yeah, you can use that in a nuclear power plant. All right. But yeah, that's what we did. And so there's Graham's law right there. So maybe it's not useless after all. I guess there's some things you can do there. All right. Okay. Best story I got, by the way. Okay. Don't know if I told it real well, but that's the best story I got. So I actually saved it for last for you. So I'm not leaving anything on the table here. I'm putting it all out there for you. I'll have to come up with something new next semester, I guess, right? Okay. Well, last thing. Okay. We talked about the ideal gas law. We said that what? PV equals nRT. And we said, yeah, that works for any gas. All gases work. It doesn't matter if it's oxygen, nitrogen, whatever. P times V is equal to nRT, right? Well, I have a confession to make. I've kind of been lying to you. It wasn't much. It was a little white lie. It wasn't that bad. But does it really matter if it's nitrogen or oxygen, or helium or argon? Can I just say PV equals nRT and that works always? Well, no, it doesn't. Does it work 85% of the time? Yes, actually it does. And so that's why we teach you PV equals nRT, because yeah, it works most of the time. But there are cases where it does matter that nitrogen is nitrogen and oxygen is oxygen. So how do real gases differ from what we call ideal gases? Well, here's the problem. When you derive the ideal gas law, what you do is you assume that the little molecules have zero volume. In other words, they're mathematical points in space. All right, and they're kind of bouncing around. Okay, you're also assuming that they don't attract each other. Okay, they're like pool balls on the table, like in our pool example there, where the one ball doesn't really attract the 7 ball. They just go by each other, and the only way they affect each other is that they hit. But is that really true? Well, no, it's not really true. Okay, real gases deviate at least slightly from the ideal gas law because of 2 factors. All right, the first factor is gas molecules do attract each other. Okay, they're not like pool balls on a table. All right, the second factor is gas molecules do occupy a finite volume. In other words, they actually do take up space. Now, why can I ignore those 2 things and get away with it 85–90% of the time? Well, if you'll remember our conceptual model of a gas, my little pool balls flying around on the table, they're generally pretty far from each other. Remember that a gas has very, very low density on the gram per liter scale, not the gram per milliliter scale like we saw in our calculation there. And so if my molecules are very, very far apart, generally speaking, they're not going to attract each other. See? And so I can ignore that attraction, and I can get away with it 85–90% of the time. Are gas molecules mathematical points with zero volume? No, that's not really true either. Gas molecules do take up space because they're 3-dimensional things, just like you and me. But the question is, do they take up a lot of space? Well, no, not really. 99% of the gas is just empty space. It's like our racquetball court example. I've got a big giant racquetball court, and I've got 3 racquetballs bouncing around in there all over the place. So let's say, for example, I have a racquetball court with a volume of 10,000 cubic feet. I don't know, I'm just throwing a number out there. Okay? And let's say I throw 1 racquetball in the racquetball court. How much room does that second racquetball have to roam around in? Well, I guess technically what? 10,000 cubic feet minus the volume of the other racquetball? Because I can't put 2 racquetballs in the same space at the same time. But in the grand scheme of things, that is essentially equal to what? 10,000 cubic feet. Because that other racquetball takes up so little space next to the space of the entire racquetball court, I can pretty much ignore that, right? What if I had a racquetball court half filled with racquetballs? How much room does the next racquetball have to roam around in? Well, it doesn't have 10,000 cubic feet. It's only got roughly what, 5,000 maybe cubic feet? Okay, because the other racquetballs are taking up a lot of space. Well, that's the situation we find ourselves in. We can get away with our oversimplification because the molecules are very far apart from each other and it's very, very low density. So the amount of excluded volume by the actual molecule itself is just practically nothing. And the molecular attraction between the 2 gases is practically nothing as well. However, both of those factors become important when your molecules are close together. If your molecules are really close together, then what that means is they're going to attract each other more. It's like taking 2 magnets and putting them closer together. And also, if they're close together, that means higher density. And higher density means more excluded volume. In other words, the volume of the molecules themselves does make a difference. So under what conditions would I find that, where my molecules are close together? Well, high pressure, to see if I squeeze in on a gas, the molecules are going to get closer together. So high pressure situations is a problem. And also lower temperature. See, at lower temperatures, your molecules aren't moving as fast, and so they're going to kind of pull in and they're going to attract each other more. I'm going to have higher density if I do that because my volume is going down. See? All right? So the ideal gas law works absolutely wonderful at high temperatures and low pressures. All right? The way I tend to remember it is the further away, the more gas-like it is. The further you are away from the liquid phase, the better the ideal gas law works. All right? So, for example, I've got water. Water boils at 100 degrees Celsius at 1 atmosphere, right? Well, where would water behave more ideally? At 300 degrees Celsius or at 102 degrees Celsius? Well, 300. See, you're further away from the liquid range. So that's where PV equals nRT works absolutely wonderful. It may differ out there in the 16th decimal place, but hey, you don't need 60 decimal places. That's okay. So yeah, we just use PV equals RT, and that works 90% of the time. But there are cases where it doesn't, and that's when you are closer to the liquid phase. And that would be like under high pressure and also low temperature. So what am I going to do if I'm close to the liquid phase, if I can't use PV equals nRT? Well, what I need is a better gas law. Okay, and that better gas law is this little guy right here, and this is called van der Waals equation. And van der Waals equation, here's your pressure, here's your volume, there's your moles, there's RT. But you got a little bit of difference here. You got this A here, and you got this B here. Okay, A and B are coefficients that are valid for a particular gas, and they're experimentally measured. So for example, if I'm dealing with nitrogen, I can look up in a chart a value for A and B for nitrogen. I can plug it in this equation, and suddenly my equation here is customized for nitrogen. Or if I'm dealing with CO2, I can look up A and B in a chart on those, and then plug it in here, and all of a sudden I've got an equation that is actually customized for CO2. So I can actually work with each individual gas instead of just saying all gases are exactly the same. Because in reality, they're not quite all the same. They're close, but they're not all the same. All right? These values are experimentally determined. This is called an empirical equation. It has experimental data built into it. Sometimes when you have something that you don't really quite understand, you don't have to understand it completely to be able to use it. You may not understand quantum mechanics and how the fluorescent lights work when you turn on that switch in the room, but you can still turn on the switch. All right. If we have things that we don't quite understand, sometimes we can account for them. And that's what this A and B are. And these would have to be looked up. You can't figure these out. Okay. And they're not even figured out. They're experimentally determined is what they would be. So you look these up and you just kind of plug them in. Okay. And this is what van der Waals equation looks like. Notice that van der Waals equation is more complicated than PV equals nRT. But look at the structure here. Do you see how it's really similar to the ideal gas law? P times V is equal to nRT. But there's a difference here. I've got this n squared A over V squared term here. By the way, how would you like to try to solve this for V? Doesn't that look like a lot of fun? Yeah. What is this? Well, this is your pressure correction term. Okay, and what this term corrects for is corrects for the fact that gas molecules do attract each other. Different molecules attract each other at different rates. Nonpolar molecules maybe not as much as polar molecules. So it goes back to polarity there as well. You get into that again. And so therefore you'll have different values for A for a different gas. But this is your attraction, molecular attraction correction term right here. Okay, this minus NB, this corrects for the fact that gas molecules do occupy space. All right, B is approximately equal here to the molar volume of your molecules. In other words, not how much 1 mole of a gas takes up, but if you looked at all the little tiny molecules in that 1 mole of gas, and you added up all their little tiny volumes, how much space they take up, that's essentially kind of what B is. So you have some large molecules, you have some small molecules. So they're going to have different values here for B. All right, and that's your volume correction term. See, the true volume is the volume minus whatever space the molecules themselves are taking up. And that's what this term over here is. All right, and you can plug numbers into this equation right here, and this is a better ideal gas law. All right, you can get answers that are more accurate here with van der Waals equation than you can with PV equals nRT. What's the problem with it? What's more complicated? I got to have this A and B, and then I got to solve for this and solve for that. PV equals nRT is really easy to use. 90% of the time, you'll get practically the same answer with either one. Either one works just fine. You don't need van der Waals equation. And that's why we've been using PV equals nRT, this whole chapter. But you need something for the times when it doesn't work. 5% of the time, right? Or 10% of the time. And that's what van der Waals equation does. So generally speaking, van der Waals equation will get you a more accurate answer than PV equals nRT, the ideal gas law. It's just a question of how accurate do I really need it. Do I need it out to the 16th decimal place, where the 4th decimal place might be just fine? Go with PV equals nRT. So it was a lie, but it was a white lie. So hopefully you'll forgive me on that one. All right. This is van der Waals equation. When you see it, you need to recognize it as van der Waals equation. You need to know that ideal gas law does not work well when the molecules are close together. That's when van der Waals equation works better. So van der Waals equation works better. Well, it always works better, but it works much better closer to the liquid phase. So closer to the liquid phase, that would mean at low temperatures and very high pressures where your molecules are close together. The ideal gas law works just great at high temperatures and also at low pressures where your molecules are very far apart. Both of those equations will give you essentially the same answer. Okay? N squared A over V squared, this corrects for the fact that gas molecules do attract each other. NB here, your volume correction term, corrects for the fact that gas molecules occupy space. If you can know that about van der Waals equation and real gases, you're going to be just fine on this test. Okay? Now, quick side note here. Are there cases where the ideal gas law gives you a better answer than the van der Waals equation? Yes. Actually, there is a certain pressure and temperature where you actually get a better answer with the ideal gas law than you do with van der Waals equation. And it tends to be pretty high pressure up there. And the reason why is because it's like, when you make two mistakes, generally speaking, when you make two mistakes, they don't cancel each other out. They tend to reinforce, right? And you end up with even worse grade. Well, there is a certain pressure and temperature up there fairly high where the ideal gas law kind of undershoots it on this one over here, but it kind of overshoots it on there, and it actually turns out to be just right. Okay, but that's a very special exception to the rule. At medium high pressures, PV over RT here is lower than what you would get from the ideal gas law, and that's because your molecules are attracting each other. At really, really high pressures, PV equals nRT is higher than ideal, because now your molecular volume becomes an issue because your molecules are really, really close together. But somewhere in between here and here, those cancel each other out, and you actually get a better answer than van der Waals equation. But 99.9% of the time, van der Waals equation will give you a better answer. It's just a question of, do you really need it that good? Sometimes you do, but most of the time you don't. And so we just use PV equals RT. I'm not going to make you calculate anything with van der Waals equation. Everything we do will be ideal gas law. But know it exists, know what it is, know what the terms here, correction terms, are for, and when the ideal gas law works best, and when it works not so well. And if you can know that, then that's you're great in that section right there. Okay? Okay. Well, I guess that's it. That's chapter 9. So I would say I'll see you next time, but I guess I really won't see you next time now, because that's pretty much it. So that's all the material that you're going to need on the file. You have finally reached the end. Congratulations. And so good luck on your file, and you have a great summer. And good luck in Chem 2. Maybe I'll see you in Chem 2 if you happen to be taking it when I'm teaching it, or maybe you'll see Dr. Pat or Dr. Reddy. They do a really excellent job. I think you're going to be just fine. If you have any questions over everything, please don't hesitate to contact me. Let's get you a good grade on this file. Because remember, if you can do better than your worst test grade on the file, it counts, but it also counts and replaces that worst test grade. But your final does count. If you do bad on this, it's going to count. This is not an exhibition. But it will only count once if it's your worst test grade. But still, I think most of you, it'd be nice if you could finish with an A, right? So, that's it. I guess I won't see you next time. But I'm around. So email me if you have any problems. Come by and see me in lab, or come by the office sometime, maybe. If you after you graduate or after you get through this course, you just want to stop by and say hi. We're all around. So I guess I'll see you around the building. Good luck. Bye.